Chem 115 students, here comes your next mini lecture on partial pressures. This one will be shorter because it doesn't require as many slow calculations as the last one with the gas laws. Gas laws do take time and practice to be careful, but this one about partial pressures isn't quite as tedious, I hope. This was described in Chem Activity 26 to some extent in your Poke Book. And let's elaborate it on a little bit more. When there's a combination of gases in a mixture, which is not uncommon, the contribution to the total pressure from each individual gas gives you the sum, put them together gives you the total pressure. So add up the individual pressures, you get a total pressure. The relationship of pressure and volume in the same container tells you that pressure 1 is related to number of moles, number 1, in the same volume and at the same temperature. So pressure 1 divided by is in a ratio to the number of moles equals RT over V. We use this to calculate partial pressures of gases in air, other mixtures, and using the total pressure and percent composition, we can come up with one and the other. So let's see how that works. All right, this one is from the text, and it's not very tricky, but it's worth talking our way through it just to make sure you see it. One way of representing gases is to use colorful spheres in the diagram like this. And if you want to use partial pressures in this particular example, the blue gas, so blue is going to have a pressure of 240 millimeters of mercury. Aha, different unit this time. And based on that, you can come up with the total pressure and the pressures of the red and the yellow gas because of the nature of the way the diagram is represented. So the pressure of the red and the pressure of yellow we will determine. The blue is what fraction or what portion of what you see here. There are 4 spheres that are blue. And the red, if you look in the diagram, use your counting fingers, you'll determine there are 6 molecules or particles of red gas. And the pressure of the yellow is going to be related to how many of those are present, and there's only 2 of those. So that relates to the total pressure. The total pressure is going to be related to the sum of the individual pressures. So the total pressure would be out of a total number of particles proportional to 12 in this case, just because that's how it's represented in the diagram. And so the blue molecules are only a fraction of it. The blue is 4 out of 12, or what do you think about that? Think fast with your mathematical skills, and you'll remember that 4 out of 12 is 1/3. So 1/3 of the total pressure is the pressure of the blue gas. That gives us something to work with. So that tells you that the total pressure must be 3 times as much as that, and so total pressure is going to be 3 times the 240. Well, math whizzes, can you do this one? This one isn't bad, but use your calculator, you'll be there, and you'll determine that the pressure total for the system in this diagram is 720 millimeters of mercury. We will verify that this fits with those other 2 gases in the mixture. Now, using that piece of information and counting the spheres, the red ones are 6 out of 12. So that's only half of the gas is going to be the red gas, and so it's going to be 1/2 of the total, and 1/2 of the total being 720, you can determine that the pressure of the red gas should be half of 320 is 720, I can't say the names, is 360 millimeters of mercury. So far, so good. Now, let's come back to the yellow one. The yellow gas had 2 spheres out of the total in the diagram being 12, and 2 out of 12 will be 1/6 of the total pressure, and lucky for you, I can pause for a sneeze and for writing. So 1/6 of 720, 6 into 720, that should be same as 6 into 72, relates to the same idea. And the answer would be 120 millimeters of mercury for the yellow gas. Now, does this still fit with the idea that the total pressure is the sum of the pressures of the individual gases? In fact, it should, if you look at this the way I've set it up. The pressure of the blue is 240. The pressure of the red was 360. Combine that with the pressure of the yellow as 120, and those do add up to the total pressure that we calculated for this mixture being 720. Time for another example. Here's one with helium and xenon with pretty green and blue colors in the diagram. The helium has a molecular weight that's much smaller than that of the xenon. The temperature is given at a certain value of 300 Kelvin, which might not matter here, but we'll see. And the total pressure of the mixture is given to be 750 millimeters of mercury. They tend to use millimeters of mercury in these partial pressure questions. What are the partial pressures of each of the gases? What does temperature have to do with this? Does not matter. Not applicable. Do not worry. So the total pressure has to be related to the partial pressure of the gases. And again, this is a counting spheres exercise, so get out your little counting thinkers. And we'll see how many blue ones we've got. I would say there must be 1, 2, 3, 4, 5, 6, 7, 8 are helium. The green are 1, 2, 3, 4, so that would be a total of 12 spheres in the diagram. The total pressure then is related to the two portions combined here. Apparently, there's twice as many helium as there are of xenon, so what? It's just numbers. And so there's 1/3 of the mixture is xenon, and 2/3 of the mixture, or 8/12, is helium. So the pressure of the helium is going to be 2/3 of the total pressure. And so we'll put in some numbers here. 2/3 of the total, and the total being 750. See if you got your math with properties going here. What's 2/3 of 750? I hope it's 500. 1/3 is going to be 250, so take 2 of those. And so that's the pressure of the helium for this example. And to do the same idea with the xenon, and we'll calculate the same idea. So the pressure of the xenon, again, it's 1/3 of the total pressure because it's 1/3 of the particles in the mixture, and 1/3 of the total pressure. I'm writing this one out more carefully. The first one I did more of a shortcut than perhaps I should have, remembering that the total pressure was given in the question up in the paragraph above. So the 1/3 of the total pressure is 750 divided by 3. Again, not tricky math. I think you can do this. What if you got 3/4? You've got 75 cents. So 1/3 of 750 should be 250 millimeters of mercury for the pressure of the xenon. Again, these two add up to make the total pressure of the mixture of the gases in this example, 750. Should always work if you've got a mixture and you've got all the parts involved. Okay, we'll try a couple more examples. This one's not bad, but it's a variation on how these partial pressures are done. If you have a vessel with a total pressure given at 20 atmospheres, so that's total pressure. And again, labeling your parts is always wise. You got a test question or a homework question, write them down. Mark them, circle them, label them everywhere you can. With oxygen and nitrogen, given the pressure of the oxygen to be 4.5 atmospheres, what's the pressure of the nitrogen? Well, it should be related to the total pressure. And if the total pressure is the sum of the individual parts, take the total pressure minus the pressure of the oxygen, and you will have the pressure of the nitrogen. And so, simple enough, we'll take 20 atmospheres minus 4.5 atmospheres, and those are the values shown in the question. Simple math, wonder of wonders, and the answer is 15.5 atm, atmospheres. Oh good, I didn't have millimeters of mercury this time, for the pressure of the nitrogen gas. One simple way of doing this. Sometimes they're just adding and subtracting. The other way to take a question like this is determine what the percent of the oxygen or nitrogen are in this mixture. So the percent of the oxygen is 4.5 atmospheres out of the total pressure, and so that's the 20 atmospheres. So the percentage of the oxygen will be calculated from that basis. And obviously, if you do this correctly, you have to multiply times 100 to get a value that's percent. And that'll be for the oxygen. That will give you a value for the oxygen. When you calculate it out, the pressure of the nitrogen is calculated in analogous fashion, where you take the pressure of the nitrogen out of, oh, sorry, I meant percent. Wrong number. Percent here. That's what we were looking for. Percent, not pressure. We did that already. Excuse my oversight. Percent of the nitrogen is the 15.5 out of 20 total pressure atmospheres in each case. And putting your numbers in your calculator, what do we get here? Oops, sorry, got to multiply by 100. Didn't mean to be skipping the step because I do that in my head. Some of you may as well. It's a worthy reminder to remember that that's part of the process of coming up with percents in calculations. I'll do these both in my calculation. You do yours as well. The numbers I got were 22.5 for the oxygen, 77.5 for the nitrogen. Those are actually not real particularly unusual, as may become more obvious in the next couple of examples. All right, so if you're looking at the gases in the mixture in your lungs, there's going to be a variety of things in the alveoli, the little air sacs within your lungs, and they're going to be measured in different quantities and given from this question. You have apparently 570 millimeters of mercury for the nitrogen. Hot water is a small portion of it, 47 millimeters of mercury. CO2 is part of it. The question then is, what is the pressure of the oxygen in your lungs? You have to use in this question realizing, or relate to, the overall pressure in the system is related to the outside pressure, the barometric pressure, 0.973 atmosphere, to come up with the pressure of the O2 in the alveoli. Not so bad, but it may seem bewildering at first. What in the world are we doing with atmospheres and millimeters of mercury? And so the point of it is, all of these pressures have to add up to the total pressure. The 0.973 is the total pressure, but it's in the wrong units. So let's convert that one into millimeters of mercury. So pressure total, I will abbreviate TOT, is going to be 0.973. All right, now what's the conversion factor? I hope you're getting used to these with some homework questions. 0.973 atmospheres. How do we relate to millimeters of mercury? Put it in the conversion factor. 1 atmosphere is the same thing as 760 millimeters of mercury. Again, this is a value no one needs to memorize, although most folks get used to it by the time you've completed homework on this chapter. I will provide it on the exam in case you're uncertain about what you would want to include on your note card or whether you remember the right things. Putting this one in the calculator only takes a moment. Hopefully you can do yours quickly. 0.973 times 760, and the answer is 739. Let's call it a 3 sig big value here. We're okay with that. And 739.48, so 739 is enough for millimeters of mercury. Okay, so given that for the total pressure, how do you come up with the pressure for oxygen? The pressure of the oxygen is related to the total minus all the rest of the other gases. So we're going to take the total pressure, call it 739, and try to make the writing legible. Subtract from that the sum of the other values given here, so that's 570, and that's the nitrogen. Add to that the pressure of the water, which was 47, and the pressure of the carbon dioxide, which is 40 millimeters of mercury. Putting all those together, subtract them from 739. Again, it's a little calculator step. Pause your recording to do your own calculations. If we're operating our calculator buttons efficiently, hopefully your value looks like mine, and I get a value of 82 millimeters of mercury for the pressure of the oxygen. Now, think about this for a moment and see if this seems credible to you. If you're looking at air in the lungs, and we're thinking about the amount of oxygen compared to nitrogen, water, if it's humid air, and CO2, the amount of oxygen is more than twice the amount of CO2. Does that make sense to you? Probably it doesn't, but the answer is yes, that's reasonable because you should have more more oxygen by a long shot than CO2. Because most of the air we breathe has very, very little carbon dioxide in it, and this is a lot more than the CO2 in the air, but yet the oxygen percentage should still be higher. One more calculation question. All right, so what is the percent composition of air in the lungs from the composition given these partial pressures? What do we use here? Well, these are the same kinds of things as we saw in the previous slide, except this time we're given some more information in a different set of conditions, namely that the temperature is provided and that the external pressure is 1 atmosphere. Oh, 1 atmosphere. Oh, percent composition and so forth from these partial pressures. Well, first of all, you'll have to come up with the pressure of the oxygen, and the total pressure is a little different from the last question. And so the total pressure is now 1 atmosphere, which if you want to do the conversion with a calculation, go right ahead, but I'm pretty sure that you might remember that 760 is the same thing in millimeters of mercury as 1 atmosphere. So start there, millimeters of mercury, one unit to write. And the total pressure minus the pressures of the other gases will give us the pressure of the oxygen. And so the oxygen pressure will be 760 minus those other ones added up. The sum of the other pressures, 570, 47, and 40, comes out to be 657. And subtracting that then from 760 will give us the answer that we're looking for, which is 103 in this case, a little bit different than the last page. And that's 103 is the pressure of the oxygen. So you can millimeters of mercury, of course, paying attention to units, it should still be all the same. To calculate the percent of each of the gases, you can do that, but let's just do one. So let's figure out what the percentage of oxygen is from this particular one. Percentage of oxygen is going to be then 103 millimeters of mercury out of the total pressure. And so the 103 divided by 760 gives us an answer, remembering that we have to multiply times 100 to get a percent value. And my answer is not showing correctly here. Let me recalculate. I had forgotten to multiply by 100 and I fooled myself. So the answer here is very funny looking. If you weren't paying attention to your values, it'd be 13.5, well, 13.55 something. How many sig figs, again, are appropriate to this calculation? You should always be thinking about this sort of thing, because otherwise you get yourself a number that looks incorrect, but maybe it's not because of sig figs. In this question, we have 2 digits, 1 digit, 2 digits, but when we add them up, we get to this 760 value, so that becomes our 3 sig figs. That makes legitimate sense for an answer on this question. So to report this one reasonably, I would call it to 3 sig figs, 13.6. All right, this is enough about partial pressures for today. I hope that this is helpful to you on your homework. Please make sure you ask more questions and get working on your homework efficiently so you'll be prepared for an upcoming exam. Good luck.